Good morning, everyone. Our first topic on numerical methods is on iterative numerical solutions. And under this topic, we have the first method. We have the method of successive substitution, or the MOS. So MOS is one of the methods to solve for the root of the equation using the iterative formula x equals x sub I plus 1, or the next value of x will be equal to the g of x. By the way, when we say iterative, it means that solving for the root requires repeated method or iterative method of solving the equation. To fully understand the method of successive substitution, we will be illustrating it through the example below. So we have given the function of x equals e raised to x plus 2 raised to negative x plus 2 cosine x minus 6. So to solve for the root of our example of the given equation, by the way, our given equation, let me just rewrite our equation. F of x equals 2 e raised to x plus 2 raised to negative x plus 2 cosine x minus 6. So our step 1 requires us to transform the given function into the form x equals g of x. So we need the equation to be transformed into the function of x in terms of g of x. So in order to do that, in our first example, we can have here, so we will retain here the e of x. Then we want to transform this 1 into the left side of the equation, so the negative 6 becomes positive 6. The positive 2 cosine x becomes minus 2 cosine x, and the positive 2 raised to negative x becomes minus 2 raised to negative x. Or simply, we will just rearrange the equation. E raised to x is equals to 6 minus 2 cosine x minus 2 raised to negative x. So that's where this equation came from. And since we need to transform it into the form of x equals to g of x, so in order for us to make this e raised to x into x, we need to have the ln of both sides. So we will get the ln of e raised to x is equals to ln of 6 minus 2 cosine x minus 2 raised to negative x. Getting the ln of both sides, ln of e raised to x becomes x, which is equal to ln of 6 minus 2 cosine x minus 2 raised to negative x. So that is if we wanted that x be extracted from e raised to x. But we can also derive x as a function of x in the equation using here the 2 cosine x. So if we will be getting the x in the form of d equals to g of x is in this equation, we can have the transposition So we have here, we will retain here the 2 cosine x. So the negative 6 becomes positive. The negative 2 raised to negative x becomes negative 2 raised to negative x. Then we have minus e raised to x. So we can further simplify this one. Cosine x equals to 6 minus 2 raised to negative x minus e raised to x over 2, or simply, how do we get the value of x? So we will be getting the arc cosine of both sides. So that will give us arc cosine of 6 minus 2 raised to negative x minus e raised to x all over 2 is equal to x. Is equal to x. So that is the value of our x. So step 2, we already now have our value of x. So from the previous example, our x is equal to ln of, so we will be using the x equals ln of 6 minus 2 cosine x minus 2 raised to negative x. So we will be using this equation for our value. So step 2, let's set an initial value for x and substitute it to the value of x in the function g of x. So say x equals 0.5. So 0.5 is the initial value or the given assumed to replace the value of x. So say at x equals 0.5, we have the g of x. So at x equals 0.5, our g of x will be equal to ln of 6 minus 2 cosine of 0.5 minus 2 raised to negative 0.5. Then, using our calculator, we can solve for the value of x equals how much? 1.2634847. So don't forget to set your calculator at radian values when dealing with the value of x, because our x is 0.5 and not in the angular form. It is in the radian form. So okay. Step 3. It is said here that the value of your derived g of x will now be your next value of x. So our x here will be, the next value of x will be the value of x I plus 1. So that will be your value derived 1.2634847. So that will be the next value of x, or the xi plus 1. Step number 4, also we will be filling up our Moss table. So if this is not clear, this is just I, this one is xi, this one is xi plus 1, and this one is the value of e. This value of xi 0.5, this is 0.5, is the given xi as the initial condition set in step number 2. So in xi plus 1, in step number 3, it is said that the next value or the derived value of x will be the next value of x. So that's why we have here the next value of x, which is 1.2634847. So here, by the way, in the iteration column, this is just the number of iterations. So since we are at the initial iteration, so we have here I equals 0, here the next one will be I equals 1, 2, 3, 4, and so on. So step 5 is to continue the iterations desired. Step 4. We forgot about step 4. So step 4. We have here step 3, step 4. You have to compute for the value of error. E equals absolute value of xi plus 1 minus xi. So error is just equal to absolute value of xi plus 1. So what is the value of our xi plus 1? That is 1.2634847 minus our initial value of xi, which is 0.5. So since our e here is given in absolute value, so 1 minus 0.5, that will give us 0.7634847. So that will be our value of e. And we will be filling up our Moss table. Again, the value of e, which was derived in step number 4, will just be reflected here. So that is just to clarify. Again, since Moss is an iterative method, so as mentioned in step number 3, this value that we derived from xi plus 1 will be the next value of our xi. So that's why we just copied this one here. So again, we will be performing, or we will continue to perform the equation until the derived error is achieved. So for this example, we need to arrive at an error which is equal to 0.00001. So errors can be an absolute error, relative error, or can only have the prescribed number of iterations. So in this equation, in this example, we are given an absolute error which is required for the equation, which is 0.001. So that's why we need to continue to solve the equation. So here, now let's go back to the original equation, which is x equals ln of 6 minus 2 cosine x minus 2 raised to negative x. Negative x. So again, this new value of xi will be substituted to this equation. So we have in x sub 1 or in iteration 1, x will be equal to ln of 6 minus 2 cosine of 1.2634847 minus 2 raised to negative 1.26348 and so on. So that will give you 1.60512238. So again, our error will be equal to the absolute value of your present minus previous. So 1.60512238 minus 1.26384 and so on. That will give you 0.34163764. So since this is just an absolute value, so this one is the value here and this one is the value here. And again, in the third iterative solution or in iteration number 2, this will be 1.60512238. Then you will solve again to solve for xi plus 1 and you solve for the error. So you will repeat the computation until the desired error E is equal to 0.000001. And in that case, we only stop until error equals 0.000001 21651. Is that correct? So 1, 2, 3, 4, 5, 6. Actually, this is still missing because we have not achieved 001. So we may add iterative number 14 and check if it should be, error should be less than 0.000001. You stop only until the error is lesser than the required error for the equation. So, kulang pa dyan. So, we need siguro iterative number 14, iteration number 14, or even iteration number 15. So, in order for us to arrive at the error which is lesser than the required error, which is 0.001. Then the root of the equation will be the last value of your xi plus 1. So looking back at the iteration table, the last value of our xi plus 1 is this one, so 1.82938. So that's why our root here is 1.829. 3, 6. Please take note that roots may vary depending on the equation of g of x and the degree of the function of x. So remember that in our step 1, we arrived at the value of x or the x in the form of g of x, which is equal to our first equation is x equals we have ln of 6 minus 2 cosine x minus 2 raised to negative x, and the other one we have the equation x equals r cosine of 6 minus e raised to x minus 2 raised to negative x all over 2. So it means that the root of this one, of equation 1, is different from the root that we can derive from equation 2. So the roots may vary depending on the equation of g of x and the degree of the function of x. So that's it for the method of successive substitution.